Good day, everyone. Today we're gonna present about our thermodynamic project. And the power station we choose is Tanjong Ping Power Station. Next, this is our group member. We have 4 members in our group. Next, this is the highlight. We're gonna present about the point 1, point 2, and 3. Yes. The first point is about the background Tanjong Ping Power Station. And in this figure, it shows that about the situation of the Tanjong Ping Power Station is located in Pontian, Johor, Malaysia, and operated by Malacor Corporations. And also, this is one of the largest coal-fired power plants in Malaysia. And next, the second point is about the installed capacity and generating units. So from this table, we saw that about the unit 3 are using the capacity amount with 700 megawatts. And also they are using the subcritical technology. And well, from the unit 4 is using the capacity amount with 1000 megawatts. And the unit 4 also use ultra supercritical technology. And the total installed capacity is equal to about 3100 megawatts. And next point is about the few characteristics and technical specifications. Okay, for the first table, it shows that about the few questions. Is the import sub bituminous coal is used as the primary fuel, and the coal is mainly imported from Indonesia. And besides that, the biomass coal firing has been introduced to reduce the emissions, and its usage is targeted to reach 15% by 2027. Okay, for the second table, it shows that about the fuel consumptions. First, the cost consumption rate is about between 450 tons per hour in unit 4. And its daily coal consumption is between 10800 to 12000 tons. The annual coal and consumption is approximately 5.9 million tons and it supports continuous operation of the 3100 megawatt power stations. So the main technical specifications is the plant type is using coal-fired thermal power plant, and its electricity generation is reheat breaking cycle. And the boiler is about the Calvary's coal boiler, and its cooling system is 1-2C water cooling. Okay, that's all for me.
Thank you to Jason. Let's look at our fuel logistics and sustainability transition. At peak capacity, Tanjong Ping burns 18,000 to 20,000 metric tons of premium, low sulfur, bituminous and sub-bituminous coal daily, imported via cat-sized vessels directly to our marine jetty to manage this without impacting local air or water quality. We implement strict logistical controls, which is automate mist sprayers and robust windbreaker walls, eliminate fugitive dust while 100% enclosed conveyors completely block PM10 and PM2.5 emissions. A dedicated drainage system also captures rainwater runoff to prevent acidic fuel leaks into the Johor Strait. In line with Malaysia's NETR route march towards net zero goals, we are actively executing our biomass coal-firing transition following a successful 1.5 to 2% pilot project. We are officially scaling up to a 15% biomass coal-firing target by 2027. Utilizing locally available agricultural residues like EFB pellets, palm kernel shells and sustainable wood chips to reduce our carbon footprint. Next, let's continue with solid waste management. Combusting 18,000 tons of coal yards, 1,800 tons of daily inorganic solid residues in distinct 90% is fly ash, amounting to 1,620 tons per day captured from the smoke by electrostatic precipitators, while the remaining 10% is potent ash slag from the base of the boiler due to its high silica and alumina content and low lime percentage. This is certified as Class F fly ash under ASTM C618 with more than 1.5 million metric tons of historical ash stored on site in outdoor ponds. Managing them is practical. We keep these open ponds constantly weathered to stop airborne dust from drifting into pollution, while closely monitoring them to eliminate any groundwater leaching risk of toxic heavy metals like arsenic, selenium, mercury, and lead. Sustainably, Malakoff drive a circular economy by selling this dry ash cement companies by selling this dry ash to cement companies to replace raw clicker in green concrete. Finally, looking at our air and marine waters, to tackle air quality, we combat sulfur dioxide emissions, the core driver of acid rain, using an innovative seawater flue gas desulfurization system by spraying hot flue gas against the counter current flow of naturally alkaline seawater inside an absorber tower. We neutralize the toxins. The resulting sulfates are safely oxidized into stable sulfates, entirely avoiding the needs for commercial limestone purchase and eliminating secondary giant waste. Rarely, our once-through cooling loop draws massive amount of cold water from the Johor Strait, resulting in the condenser dumping roughly 1,308 megawatts of low-quality thermal waste energy into the discharge line. This creates a localized thermal pump where the discharge water is significantly warm, experiencing a 5 Celsius to 10 Celsius temperature rise. Because increases water temperature physically reduces oxygen solubility, the thermal discharge is meticulously monitored to protect local marine health from sudden drops in dissolved oxygen. That is all for me. Thank you. I will pass it to next member.
So moving on to number 3 section. Before we look at the numbers, we first need to establish our core engineering assumption to map out the cycle correctly. So first we have steady state flow. We assume steady state flow condition, meaning that the fluid mass and energy rate inside the system remain constant over time. Second, we have kinetic and potential energy to be negligible compared to the massive change in enthalpy across the component. And lastly, we have component heat losses. We assume the turbine, pump, and piping are perfectly insulated, meaning heat transfer only happens where it's supposed to, which is inside the boiler and the condenser. So then we have the baseline operating state. So based on those assumptions, we map out the 6 key state point of the heat turbine cycle. As you can see from the table, state 1 is our peak energy state, where superheated vapor leaves the boiler at 540 Celsius and 70 megapascal. After expanding through the high pressure turbine, it drops to state 2 before going back into the reheater. So once it's reheated to state 3, it reaches 540 Celsius again at a much lower pressure before hitting the low pressure turbine. So the bottom of the cycle is managed by the condenser at stage 4 and 5, maintaining a vacuum pressure of 8 kilopascal before the pump raises it back to high pressure at stage 6 to complete the loop. Okay, so we move on to slide 3. Here is the physical layout matching the 700 milliwatt subcritical configuration at Tanjung Bin power plant. We can trace the fluid journey in 4 main steps. First, we have the energy steam exit the boiler and undergoes high pressure turbine expansion. Second, instead of going straight to the low pressure stage, the cooler exhaust steam goes through a reheat stage back in the furnace to boost overall thermal efficiency. Third, we have it hits the low pressure turbine stage, expanding all the way down to vacuum pressure, and finally it's condensed and form a continuous loop back through the feed pump into the boiler. And the last slide is about the schematic pressure enthalpy diagram, where we can see where to as you can see we start our thermodynamic price against the water vapor saturation and dome. There are 3 key visual features to note here. The double hump on the right perfectly captures our reheating process between state 2 and 3. The saturation dome itself defines the exact phase boundaries where the water transition between liquid and vapor. And finally, notice the non-ideal length on the vertical line. This shows the real world deviation from an ideal cycle representing fluid friction and entropy generation. This visual setup provides the exact properties that the next presenter will be used for our final mathematical calculation. So thank you, that's all from me.
Now let's dive into the core numbers. To evaluate the 700 megawatt subcritical unit, we established a baseline model using standard first and second law volumes, which you can see on the left. We track everything from turbine work and pump input to our main environmental indicators, condenser heat rejection and net entropy generation. On the right are our baseline conditions. To hit our net electrical target of 700 megawatts, the mechanical system actually needs to push out 714.3 megawatts to cover generator losses. This runs on a subcritical throttle pressure of 17 megapascals at 538 degrees Celsius, rejecting heat to a 300 Kelvin seawater sink. These parameters set the boundaries for our mathematical walkthrough. Moving into the math, our first step was calculating the shear volume of steam required. Based on a standard specific work output of 1150 kilojoules per kilogram, this plant requires a massive steam mass flow rate of 621.1 kilograms per second. Next, we factored in the internal energy cost to actually run the plant. The boiler feed pump alone consumes 12.52 megawatts. On top of that, auxiliary equipments like draft fans and cold pulverizers take a heavy toll, eating up roughly 6.5% of gross generation. For this unit, that's 48.1 megawatt internal power tax before we can even supply the grid. On the back end of the cycle, we calculate the energy leaving the system. By tracking enthalpy drop across the condenser, we find that a staggering 1308.04 megawatts of thermal energy is rejected directly into the cooling water. First, using the first law, we add our net mechanical power to this rejected heat, which tells us the boiler requires a thermal input rate of over 2000 to 22 megawatts. Finally, we run the entropy balance using our absolute source and sink temperatures. We get a net entropy generation rate of 2985 kilowatts per Kelvin. This is the mathematical proof of the unavoidable irreversibilities looked inside the subcritical design. So what is the real world impact of these numbers? First, our net cycle efficiency lands at 35.3%. Flip that coin over and it means nearly 65% of the coal's chemical energy is entirely lost as low-grade waste heat. The ceiling is a structural limitation. Operating at subcritical pressures forces a prolonged boiling phase change that fundamentally caps efficiency. This exact inefficiency drives our environmental risks. That 1308 megawatt thermal dumping creates massive marine plums, discharging cooling water 5 to 10 degrees hotter than ambient conditions, causes sharp drops in dissolved oxygen, threatens local sensitive ecosystems like the Pulau Kukup Ramsar mangroves. This is exactly why the industry upgraded Unit 4 to ultra supercritical technology. By pushing pressures past the 22.1 megapascal critical point, you eliminate the boiling phase entirely. This slashes daily coal consumption and drastically reduces the thermal load forced into the ocean. To wrap up, our analysis maps out a baseline 35.3% efficiency and a tight link between power generation and localized thermal footprints. These metrics underscore the urgency behind Malakoff's environmental strategies to monitor and mitigate the thermal plums. Moving forward, the vision relies on transitioning to high-efficiency ultra supercritical parameters and advancing the biomass co-firing strategy toward a 15% blend by 2027. This dual approach will allow us to successfully decouple vital baseload power from high carbon and thermal intensities. Thank you.